Hello, boys and girls. Welcome back. Once again, we're going to enjoy a little physiology lesson. This week, we're going to be talking about our kidneys, and I'm going to be going through this as thoroughly yet as quickly as I possibly can because, believe it or not, your kidneys are very important and very complicated. So, here is a representation of your kidney, this bean shape that you're familiar with. We're going to be honing in on just a little area here in the area of this kidney that we call the medulla within the outer area that you see here called the cortex. So we're going to be looking at a little at these areas. We're going to zoom in and look at what happens on a molecular level as your blood is being filtered and waste is being removed, so that you can then excrete it. So that little speck that I was pointing to is something that we call the renal corpuscle, which is this this structure that can be described as having this little ball called the Bowman's capsule, and inside of it is a little network of crisscrossing blood vessels called the glomerulus. So what I'm going to be doing is describing the process of filtration. But first, I want to paint kind of a broad picture for you. So you have your oxygenated blood coming in through this side, through your afferent arteriole, and coming out the other end from, excuse me, from the other side into the efferent arteriole. And the reason that is blue isn't necessarily because it's totally deoxygenated at this point. It's just to signify that this is where the blood is leaving. It's less oxygenated than it was before it entered the glomerulus. So here is the heart of filtration. It is in the renal corpuscle, and this whole structure here is what we call the our cortical nephron. Nephron is just this filtration unit within the box. And then we have our juxtamedullary nephron. Cortical meaning that this entire structure, this loop that you see, lies closer to the cortex, the outer part of the kidney. Juxtamedullary means closer to the medulla. Medulla is simply the inner part of the kidney, closer to the renal pelvis, you could say. So coming out of the Bowman's capsule, you see this tube coming out. We're going to go into a lot more depth in it later in this video, but just to give you a broad overview, we have our proximal convoluted tubule. We have our descending tubule, in which the 2 and 3 represents the processes of resorption into the bloodstream and secretion back into the bloodstream, respectively. And then we have our ascending tubule. We have our macula densa, which is very important. And then we have our proximal convoluted tubule, going all the way back into the collecting duct, which is step number 4 of the filtration process, you could say, which is excretion. These collecting ducts ultimately lead to the bladder and the ureter, the urethra, and then urine can be excreted out of the body. And so the pressures that dictate the filtration that goes on in the glomerulus here, if we zoom in yet even further with this cruder representation, we again have our afferent arteriole bringing in the oxygenated blood, our efferent arteriole bringing the blood back out. This is our glomerulus here. So our Bowman's capsule, and then this is our nephron, or rather the rest of our nephron. And the best way that I can summarize this is by talking about the factors that dictate what essentially forces these these filtrates, these particles, these ions that are being squeezed out of your bloodstream and uh, into the substance that you excrete, your your waste. Yeah, that's a good way. Your waste starts with hydrostatic pressure and your blood colloidal osmotic pressure, as we talked about last week's video, I believe. So hydrostatic pressure 55 is a lot higher than it usually is. That's a lot of pressure being built up. So in order to prevent these arterioles, these blood vessels from simply bursting, there's these cells called mesangial cells that essentially do this. They interlock over the top of your glomerulus and they maintain its tensile strength. They keep it from bursting. So that's just a little interesting fact for you. So hydrostatic pressure being this high obviously means that there is a lot of pressure forcing the substances floating along in your blood to be wrenched out. And then we have our this despite standing despite having the acronym CP, it actually stands for capsule pressure. It's not colloidal pressure. But the important thing to recognize is that it's a lot lower. So your substances aren't going to meet a lot of resistance as they're being excreted, depending on the channels that we find on this membrane, of course. Another principle that's important to understand when it comes to filtration is the concept of vasoconstriction. Uh, it might seem intuitive when I say it, but apparently a lot of people get confused by this. If you were to increase vasoconstriction on the afferent arteriole, perhaps right here, the hydrostatic pressure will go down because not as much blood is coming in. That would make sense, right? So what if I increase or what if I decrease the vasoconstriction? What if I experience vasodilation? Well, that's going to allow more blood to come in to the glomerulus. More blood pushing on the walls, expanding it, hydrostatic pressure is going to rise. So vasodilation, you're going to see more excretion, you could say, and with vasoconstriction, you're going to see more, or you're going to see less excretion. So that's the way, those are just a couple of ways that blood flow to the glomerulus is regulated. It's through this vasoconstriction. And the different factors that affect vasoconstriction we're going to talk about later in the video. Trust me, we're going to put all the pieces together by the end of the lesson. But the next thing I want to talk about a little bit is the GFR, the glomerular filtration rate, or how well the kidneys filter waste from the blood. So the GFR is in constant fluctuation. It cannot be measured directly. There's no instrument per se that you can hook up to your kidney and measure your GFR outright. This happens on a very small molecular scale. It's it's something that can't really be measured in real time. However, something that you can do is measure clearance through this equation here. And by clearance, we're talking about the removal of substance called inulin from your blood. And the reason why we choose inulin to measure our glomerular filtration rate is because it's a 1-to-1 ratio. As much as you ingest, you are going to excrete through your urine. If you ingest 1 gram of inulin, you're going to excrete 1 gram of inulin in time. The more water you drink, for demonstration, the faster you're going to excrete that inulin, of course. That's part of the lesson. So the amount of inulin, for example, that we have in our blood plasma as it's traveling through the glomerulus is represented by px here, or inulin concentration of plasma. And then we have our inulin concentration in the urine. So this is our handy equation that we use to measure our glomerular filtration rate. Because rest assured, if we ingested 1 gram of inulin and we have not yet excreted it, it's going to come out at some point. So it's just a matter of how long it takes or the rate at which it's filtered through the glomerulus, hence the name. And so let's say we ingested that 1 gram, but we have only excreted half a gram. And then we also have the volume of water, that the total volume that we've excreted. So the water along with that inulin and the water, I don't know, let's say there's 5 grams or milliliters worth of water. So that would give us a glomerular filtration rate of 2.5. You can check my math on that. Yeah, please do. So this would actually be, we would actually have 1/2, I believe, because it's a total of one, right? Moving on. So that's I'm obviously not the greatest at the math, but the principle of clearance is what's used to estimate our glomerular filtration rate. So when you hear GFR, just think of clearance in the context of inulin. So next I'm going to explain something that we call tubuloglomerular feedback. This is just a form of autoregulation in the bloodstream that monitors the sodium chloride levels in the macula densa right here. So the higher our sodium chloride, the higher our salt levels are in the blood, in the macula densa, rather. There's going to be an increase of adenosine And if the levels of sodium chloride are low, that's going to lead to a decrease in nitric oxide. And the reason either of those things are relevant is because they are either going to um, they're either going to constrict the efferent arterioles or they're going to dilate the afferent arterioles. And that's going to lead to lower and higher blood pressure, respectively. And the higher our blood pressure is, the more filtration we're going to have because these particles are being forced out of the blood and into the excrement. So, again, more salt in the blood being um, detected in the macula densa means more adenosine, meaning uh, constricted efferent tubules. And if it's constricted, that's going to mean a lower blood pressure and a lower filtration rate. But if there's low salt levels, if you're drinking a ton of water, for example, you're going to have decreased adenosine and you're going to have decreased nitric oxide, which causes dilated afferent tubules. This is going to lead to an increase in hydrostatic pressure and more filtration. So, yeah, lower salt essentially means you're going to experience less blood pressure. That's pretty intuitive, right? Okay, we're cruising along. That was about half of our lessons so far. Maybe more like a third. But next, we're going to talk about uh, the kidney tubules. We're going to be talking about solutes and water. So this is just another way of talking about what we did up here, just a different way of looking at it. This is our kidney right here, this big box. This is our bladder down here. 20% of our cardiac output, or the blood that we pump out of our heart and down through the aorta, is going to go straight to the kidney. There's a ton of blood that goes down to the kidneys. And excuse me, it makes sense because this is what's keeping our blood clean. This is what's removing the waste from it and the unwanted ions, like the inulin that we have absolutely no use for. So here's our filtration. We have some ion channels that allow specific charged particles to enter into the kidney. Since there is, this is the aorta, since there are so many cations, positively charged ions flowing through the bloodstream and less so built up inside of the kidneys, because we have a lot of proteins in here that are negatively charged because of phosphate groups adding up, you're going to see some repulsion of negative ions. There's a bit of a negativity force field keeping negative ions out of the kidney. There's also a size limit. You have to be around 6 to 15 nanometers in diameter to be able to enter into the kidney through these channels. So this is the filtration stage. Things getting filtered into the kidney through the blood, things like sodium and um, similar ions, which we're going to be talking about down here. We got a giant mess down here to unpack still. Here's resorption. Certain solutes and water are resorbed through the kidney tubules and into the bloodstream. which is a good thing. We don't want to excrete all of the water that we ingest, right? We want to keep the rest of our bodies lubricated and then get rid of it only when we absolutely have to. And the interesting thing about water is that our body will, we're adapted, we're acclimatized to recycle it through our bodies as much as we should need it. If you go to the desert, you'll quickly find that your body is not prepared to retain water as well as perhaps a camel would because they're adapted to that environment. They are much better at resorbing water. Humans, they are acclimatized to environments that aren't nearly as hot as the Sahara Desert. So resorption is a pretty important step. This is where uh, solutes such as sodium are resorbed back into the bloodstream, as I said, and they bring water with them. Osmosis. An important principle to understand is that we can't force water to go anywhere. We can only lead it to different places using solutes. So it can follow that chemical gradient because water goes where the party is. Next is secretion. This is uh, this is a part that I don't know if I would say it's necessarily permeable to solutes in the blood so much as there are very specific channels for things such as potassium, chloride, separately, uh, more sodium. You're going to see a lot of specific protein channels that allow for the secretion of particles from the blood into the kidney. Excuse me. And then finally, we have excretion. Once you've had waste build up enough, presumably from the bloodstream or from the kidney itself, it's going to be forced into the bladder, then into the ureters, through the urethra, and then out into the world. Okay, so I told you we had a mess down here. Here we have another crude drawing of the cortical nephron, and I'm going to be going over each of the, I guess, 5 different sections of the epithelial tubular cells, you could call them, of the nephron. So we're going to start with our proximal convoluted tubule. Um, you can probably see why they call it convoluted. So on our, so this is our FERB-shaped epithelial cell on the surface of this proximal tubule, proximal because it's closest to the glomerulus, to the Bowman's capsule, to the renal corpuscle, whatever you want to call it. And on the apical side, we have our lumen, or lumen of the kidney. And on the basal side, we have our bloodstream right back there. So, yeah, I'm just gonna jump right into it. Uh, I'm gonna not try to go too fast through this, but it's actually not quite as bad as it seems. So here we have a smorgasbord of various molecules and ions and very specific channels that allow for their their resorption into the bloodstream. This is all that these cells are talking about is resorption going from the kidney into the blood. The reason it got to the kidney in the first place is because of filtration. Spends some time in the kidney, it hangs out, then decides I'm going to be reabsorbed back into the blood. And not necessarily needed here. So here we have some Molecules that are on the larger side, such as lactate and glucose, they enter in through the epithelial cells through a symporter channel with the sodium ion. Sodium ion is basically the star of the show here. It follows a concentration gradient that needs to be maintained because of this NAC pump, this sodium potassium ATPase pump that is constantly taking this high concentration of sodium within the cell and just dumping it out as much as it can. Meanwhile, two potassium ions are coming in like a revolving door. And so to maintain high concentrations of said sodium, it's powering all sorts of pumps on the apical side. So there's always sodium getting pumped back into the bloodstream because sodium in the blood at certain levels actually is a good thing. We do need sodium. And it also powers this symporter, where in which amino acids, these essential building blocks for proteins, come through. So proteins come into the, or these amino acids come into the endothelial cell, and they're used for building proteins. We can only assume, right, through the endoplasmic reticulum. Sodium, final channel for sodium on the apical side of the proximal convoluted tubule epithelial cell is this sodium proton antiporter. This obviously does a good job of maintaining the pH gradient. It prevents the endothelial cell from becoming acidic as hydrogen cations build up. And something I forgot to mention is that both of these channels here, the potassium leak channel and the NAC ATPase, you're going to find these on every single cell here. We look around, you're going to find them on every single epithelial cell. Also, there are aquaporins in the proximal convoluted tubule, simply meaning that water goes out of the kidney and into the bloodstream without basically any resistance at all. Water just walks in and out at no energy cost. It just diffuses as it pleases. It has the easiest time. And then finally, to defeat this monster of a cell, we have this this protein called carbonic anhydrase. It takes H plus, it takes protons and bicarbonate HCO3 minus and creates H2O and CO2, carbon dioxide. We have carbonic anhydrase within the cell and also on the outside of the cell doing the same thing. It takes so to prevent too much acidity from building up on the outside of the cell, it will take available bicarbonate and do the same thing out here, creating water, which can then go through the cell again, and then CO2, which will eventually get caught up in the blood again and then exhaled through your lungs. So that's what carbonic anhydrase does. And it does the reverse too. There's equilibrium to be had. Of course, it can go either way. It can turn CO2 and H2O back into proton and bicarb. So moving down this tubule, we have our proximal straight tubule around the bend. On the basal side, we have sodium going from the kidney, from the, yeah, coming from inside the kidney and going back into the blood, being resorbed, as we saw before with the proton antiporter. And then we have an anion chloride pump, which is interesting to me. We were taught was an H or a hydrogen anion. And this is also an antiporter. So the chloride comes into the epithelial cells, excuse me, and there's a leak channel on the other side, at the apical side, getting resorbed into the blood. And anions, as far as I'm concerned, they essentially diffuse, kind of like we talked about up here. They just automatically get filtered. Filtered meaning they're selected because they're the right size, they're negatively charged, they don't meet a lot of resistance, so they can diffuse. So there's kind of this constant game of back and forth that's powering this chloride antiporter, so it can be resorbed into the blood. Pretty cool. And this channel is actually called the cystic fibrosis transmembrane regulator. And when these become deactivated or cannot sufficiently work at a large enough scale, that's actually what causes mucus to build up in your lungs, and you're constantly hacking it up, and you have a very hard time breathing. So, if you know someone with cystic fibrosis, this is what is wrong with their cells, their kidney cells. Found that pretty interesting. So, this is what we call our descending tubule or our descending loop. This is called the loop of Henle, by the way. We're going to talk about it a little bit more. And this is probably the simplest of all epithelial cells. It simply just has aquaporins on top of the neck pump and the potassium leakage gate. And the interesting thing about water up until this point, this first half of the epithelial cells, you could say, is that it can either go transcellularly or it can go, the word's escaping me right now, or paracellularly. Para meaning around, trans meaning across. So we have our aquaporins here, transcellular, paracellular, through these sort of gap junctions, if you will, in between the next epithelial cell. So they're just kind of stacked on top of each other. And represent it like this. So you got your basal side and then you got your apical side over here. So yeah, you're gonna see some solute dragging. It's pretty late over here. Some solute dragging going on. Actually, water is gonna wash certain um, ions along with it. Okay, and then as we're going through the ascending tubule, we hit that curve. You're no longer going to see any paracellular movement by water or ions. It's going to bounce right off. This is supposed to be a little water drop. And this ascending tubule or ascending loop is going to have a single channel that we're concerned with. It's just a triple symporter. It's going to bring over one potassium ion, one sodium ion, and two chloride ions. The chloride ion still has its own leakage channel, just as it did up here. And you have your, of course, means of removing sodium and potassium. Excuse me, as I said before, or as I alluded to before, I should say, anything that remains on this side of the epithelial cell or remains in the lumen of the kidney is eventually going to be excreted out. So let's say this channel, this triple symporter gets blocked. None of these three ions can get through. They're trapped in the kidney. Oh no. they're going to get peed out. Needless, just to put it bluntly, they're going to get excreted. And this action is achieved by drugs called diuretics. Essentially, just means to make you urinate more. And the more of a concentration that you have built up in your pee, the more water gets dragged out of your bloodstream because water osmosizes, emits osmosis to follow that solute, and you're naturally going to want to pee more. Very interesting stuff. Going up through the macula densa, where we talked about the detection of sodium chloride levels, it's only fitting that there is a sodium and chloride symporter channel. And if there are very high sodium chloride rates being detected, that's going to trigger our, I'll bring us back up here. Where was it? Where was I talking about it? Oh, I think it was just the macula densa right here. Yeah. So more NaCl being detected in the macula densa. I didn't write it down, but it means increased adenosine and higher blood pressure and more glomerular filtration. So you're going to pee more in an effort to lower those sodium and chloride levels that are being filtered through, or rather, that are being resorbed. Okay. Finally, we're going to go over one last epithelial cell, and we will be more than halfway done. So this is called the distal convoluted tubule, proximal convoluted, distal convoluted, because they're very complicated. We still have our stitched up gaps. There's no water or ions going through paracellularly. No more taking shortcuts. We have some potassium and sodium channels that are open. They pretty much just allow free diffusion. And then there is a also aquaporins. So this is a pretty relaxed, unguarded sort of deal. These ions are being excreted. If they were really needed at this point, they already would have been reabsorbed. So they just kind of, there's a very low milliosmolarity going on out here. It's like at a 100, I believe, off the top of my head. Whereas regularly it's 300 or above. So there's not a lot of pressure forcing anything to move in a particular direction. So something I want to tell you about is aldosterone, which is a hormone, a steroid specifically, that leads to increase of antidiuretic hormone levels in your bloodstream. And when that builds up enough, that increases the chance of said hormone being received by an ADH receptor. ADHR, this is a G protein coupled receptor that begins a signaling pathway. And all that's really important to know about it is that it activates this little vesicle, this ring, just entirely made of aquaporins, from what I understand, or it creates aquaporins and donates them to the basal side or sorry, the apical side of the epithelial cell. So the more aldosterone that you have in your body, the more antidiuretic hormone you get, meaning more aquaporins on the side of your kidney, meaning less is going to be excreted because the ureter, your can't speak right now, your your bladder isn't going to be able to excrete as much water because it's being filtered back through the epithelial cells and into the bloodstream. And your blood pressure is going to rise because of that. Your blood volume is going to increase all the more. But there are some reasons where you do need antidiuretic hormone. Perhaps you're severely dehydrated and you need to recover quickly. Okay, before moving on, real quick, I'm going to address something called renal threshold and saturation. Saturation is the principle that powers renal threshold. I guess you could say they're kind of one and the same. Basically, renal threshold is alluding to the maximum concentration that a solute can have in your blood plasma. So, for example, in the glomerulus here, before it can no longer overcome its own saturation and is just forced out. No matter how badly it doesn't want to go, it becomes excreted. So a high enough saturation of chloride, for example, in the blood will cause, so all of these negative ions are bouncing around, repelling each other. If they're all crammed in there, if there's such a saturation to the point where they cannot just simply all pass through back through the efferent arteriole, they're of course going to squeeze out of the glomerulus and then be excreted in the urine. That's pretty much simple as that. Moving on, I want to talk about something that really interests me. This is called the RAS system, or the renin angiotensin aldosterone system. And if you didn't quite understand the role of aldosterone before, we're going to talk about it a little more here. So let's say that your glomerular filtration rate is really low. Let's say that you get pinched in your afferent arteriole for whatever reason. You have high vasoconstriction, and as we talked about earlier, that's going to lower your hydrostatic pressure. Not as many things are going to be, uh, can never get good verbs. Not as many solutes are going to be wrenched out into the urine here, wrenched out of the blood plasma. And so your low glomerular filtration rate, solutes getting filtered out of the bloodstream and into the kidney, is going to result in an increase of production of this enzyme that's called renin. Renin because it's produced in the renal gland, or the kidney. And more renin enzyme is going to lead to the production of yet another enzyme called angiotensinogen, which leads to the production of angiotensin 1, then angiotensin 2. Each of these things have um, specific roles, of course, being precursors to yet another enzyme. But that's because you can't turn renin to angiotensin 2 in a single step. It has to go through a process. It's ordered sequential. So if you're ever wondering why there's a bunch of intermediates, you can't just add everything at once. It's like Legos, you gotta go one at a time. Angiotensin 2, with an increased pressure presence, is going to increase blood pressure. And how's it going to do that? It's going to do that through telling your brain that you're thirsty. It's going to ask you to drink more water. So, for example, I have a lot of angiotensin 2 built up in my body right now. I have a very low glomerular filtration rate. I have very high renin, angiotensin, and angiotensinogen. And so my I have a buildup of thirst. I have more antidiuretic hormone. That's my body saying, hey, uh, we shouldn't be excreting as much water as we usually do because our blood pressure is high, or rather, because we don't have enough water in our bloodstream. And the baroreceptors, kind of like we talked about, almost forgot the name for a second. Baroreceptors, or the pressure, the basically the metric of pressure in our arterioles surrounding our kidneys, similar case in our heart. They aren't super sensitive, but they're sort of our first line of defense if they see that there is a decrease in GFR. Uh, the baroreceptors are going to trigger a response of more ADH. And then you also have your osmoreceptors, which measure the rate of osmosis. These have to do with your brain, and they are very sensitive. So the smallest change of blood volume or the level of water in your blood is going to go right to your brain, and your brain is going to recognize that you're thirsty before your body is the best way I can describe it. So more antidiuretic hormone equals more vasoconstriction and more dilation of the afferent arteriole. We go back up here. So if we dilate, we have vasodilation. We're gonna have more blood coming in. Now I'm thinking about it, it would actually be constriction of the afferent arteriole. And the reason why is because if you pinch this off, the afferent arteriole, the hydrostatic pressure is going to decrease and you're not going to get as much water excreted out of the body. So that's why I wrote that down wrong. Apologies. And then there's also aldosterone. Aldosterone leads to hyperkalemia. Aldosterone. So the more ADH is being received by this GCPR, the less we are going to have a gradient of potassium. Naturally, within cells, we have a very high difference intracellularly and extracellularly, but the more aquaporins we have, the more drag of the ions we're going to see into the cell. And so, oh, okay, not into the cell. The water actually is going to drag them out. My bad. Hyperkalemia is referring to in the extracellular fluid closer to the blood, high potassium blood levels. Yeah, so the more aldosterone we have, the more actually you're going to have potassium forced out of the cell, if only by virtue of having all of these aquaporins causing water to flood into the cell and force the potassium out. almost like an antiporter action, I guess you could say. Okay, all right. Just a couple more things, and then I can let you get on with your night. Thank you for being patient with me. This was a super dense lesson. As I'm going to go back to talking a little bit on the loop of Henle. Loop of Henle consists of our descending and ascending tubules. And the way that it really establishes and maintains uh, concentration gradients in the renal medulla. So you could look at our juxtamedullary, our nephron here, is it just reabsorbs ions in the ascending limb and it creates a hypertonic environment in the medulla, kind of right here in this area. And I also drew it down here. Let's say if we kind of twisted the loop of Henle so that it's not wrapping around itself. So you have your glomerulus here. You have your descending convoluted tubule after your, um, or sorry, proximal convoluted tubule and your proximal straight tubule, descending tubule, ascending tubule, and the, I guess this would be your macula densa here because it'd be linking up with your glomerulus again, and this would be your distal convoluted tubule. So the descending limb here is the only part that is permeable to water. So you're going to see a pretty consistent, uh, let's see if I can. So you're going to see water just passing right through, totally permeable. You're going to see transcellular and paracellular action going on. And it's permeable all the way down. You got your straight tubules that are less permeable, but still you get the paracellular action going on between them. And then you have your descending tubule. They both have paracellular and transcellular. And as you're going down, you're going to get different levels of millosmolarity. And it's going to be slightly higher, if I understand correctly, on the inside of the descending tubule. I just want to make sure what I'm telling you guys is correct here. Yeah. It's actually going to be balanced very well because we have this free movement of water crossing the membrane and balancing with the ions on the outside. The deeper you go into the medulla, the more higher concentration of ions you're going to have. As you go higher, the less concentrated it's going to get. And since this is completely permeable to water, or at least a lot more permeable relatively than the rest of the nephron, you're going to see a consistent gradient because it starts at 300 and 600 milliosmolars in terms of concentration. So it doubles as it goes. It's kind of like water pressure building as you go deeper in a submarine. However, as you observed and as we talked about earlier, as we traveled through the ascending tubule and the macula densa distal convoluted tubule, we no longer get paracellular or transcellular action, really, save for this very final convoluted tubule with the water. There's very limited restricted water movement going on in the second half of the nephron of the loop of Henle, at least. Yeah, that's really the loop of Henle is all that we're really concerned about now anyway. So I'll just say water isn't permeable anymore, but ions are. So it's going to kind of be stuck behind. It's going to have the ions filtered out quite a bit faster. And there's no equilibrium of water going on to maintain this. So this 600, as it begins to rise back up, very quickly becomes 400 milliosmolars. I was just checking my numbers for you guys because I don't want to feed you misinformation about specific numbers. So you see a very sudden drop in the concentration of ions as we ascend the loop of Henle again. And that means that ultimately in the collecting duct here at the end of our nephron, you're not going to see a ton of solutes in your urine again, but you are going to see more water. You're going to see more aquaporins coming in the collecting ducts. So you're going to see your milliosmolars increase back up to 600. So hypertonic, meaning that it becomes pretty salty, becomes pretty salty in this area in the medulla surrounding the um, excuse me, ascending tubule, ascending loop of Henle. All the water is essentially sucked out at this point. Okay, finally, the last thing I'm going to talk about is the gradient, this chemical gradient that we talked about, as well as antidiuretic hormone, working together to excrete urine of varying concentrations because of the amount of water that's getting reabsorbed. So it follows intuitively, the more water that's reabsorbed here, the less is going to be excreted. The more of a high concentration of solutes that you have in the kidneys or remains in the let's see, remains in the kidneys, the more water is going to stay and be excreted. Or water may be it may be reabsorbed into the blood to follow a higher concentration gradient in the blood, and such as hyperkalemia. So I hope that wasn't too scatterbrained, you guys. That was a massive lesson. We've talked about a lot. The kidneys are pretty complicated. Uh, I wish I was able to see you guys and you could ask me questions to clarify anything if need be. I'm sure there are a couple of questions floating around out there, but um, did my best to illustrate this for you guys in a relatively simple way. And I hope that you came away from it having learned something. Appreciate you all for tuning in every week and hope you have a good one. Goodbye.